who made it.
I would like to thank you all for inviting us today to give you a short overview of 2226 and what we try to achieve with it. Maybe some of you heard of it. It's an energy concept, fundamentally. And unfortunately, my time is quite short. I talk about 2 hours for this topic, but now I have to hurry up and give you a short overview. So let me introduce myself. My name is Sebastian Nödl. I'm originally from Vienna. I worked as a technical project lead for 2 really famous museums in Vienna. So I have a lot of experience of indoor climate and technical and building services. But then again, I moved to Vorarlberg half a year ago to work for 2226 because I was really impressed with the energy concept. Let's head forward. You can see this is the first project we did with 2226. And the idea started when Professor Eberle, he is the head of Baumschlag Ebel-Architekten, was at a lecture in Massachusetts, and he heard a lecturer, Dr. Lars Junghans. He told him, why is it not possible to build an office building without heating, without a cooling system, and without mechanical ventilation? So he developed this idea, and further developed it further, and this is the first project he did, which is energy concept. What is 2226? So, you see, it is a strategy to increase the comfort of the users of the building. We try to reduce the energy of the building. We lower investment costs and increase the life cycle of such buildings. Today, buildings are like 50 years in use, then they get demolished, which is unfortunate. This is an economical and ecological disaster, of course. We have to shape the future of architecture and increase the life cycle of buildings. This one, well, it should last around 100 years. Later I'll show you the layout of the building. You can see its neutrality in its use. So, here you can see the layout of the building. It is very simple, it is very elementary, it is quite simple architecture, it's nothing new actually. And down there you can see all the ventilation going in and out, but more on this later. So what I mean with to try to increase the comfort of the users, it's quite simple. You know it from home. Air gets stale because CO2 rises in the building, and you have to open the windows. So we have, in the outside air, we have about 400 ppm of CO2, and in mechanical ventilated buildings, it's about 1,000 to 1,500 ppm CO2, which is not dangerous, but it's fine, and we want to lower this, of course. So the desire for fresh air is determined by the CO2 content in the building. Then, of course, temperature inside the building, 22, 26, this is quite simple to understand. 22 is the lowest range we want to achieve, and 26 degrees Celsius is the highest degree we want to have inside. This is what's evaluated and studied, and this is regardless of location or culture. This is always the comfort range, but it's very subjective, of course. So some girls may freeze at 22 degrees, and I'm quite hot at 22 degrees actually. Humidity is also another very important part. So we try to have like 40 to 70% relative humidity inside our buildings. During the Corona pandemic, there were lots of studies, and they found out if you go below 30%, the infection rates doubles. But you can also, of course, save energy if you go below 30%. But as a society, I think health should be the most important thing. So that's why we try to achieve 40 to 70%. Plus, we want to optimize and reduce the energy. As I said, we have no heating and no cooling system and no ventilation. And this is achieved quite simply. We used elementary styles of architecture. We have really, on this project, really big walls. It's like 80 centimeters. We have 2 bricks. One is static, one is insulating. So of course we can't do this in the city because the walls would be much too thick. But it doesn't have to be this large. You know it from castles. They have also very big walls, and in the summer it's cool inside, or like churches, it's cool inside during the summer, and it's warm if you heat an oven, for example. And this is what we use to increase the comfort, so to say. Now you may ask, what happens on hot summer days and cold winter days. As I said, we have no heating and no cooling system, of course. So hot summer days are not really a problem for us, because we calculate all the internal loads that are inside the building. So for example, one person radiates about 80 to 100 watts per hour, which is quite a lot actually, if you think about it. And also then in offices, you not only have people, you have PCs, scanners, servers, and they all produce energy and heat. And this is what we use to heat the building, which is quite simple. And also artificial lighting and solar radiation. On cold winter days, it's just a simple task for you. If you think about it, so we don't need heating, because the internal loads are so high and the walls are so massive, and also all the masses are in the walls and of course in the ceiling. We use concrete ceilings here. In the summer it's a bit different. Well, as we said, we have no cooling, so how do we cool the building? I will show you on the next slide. You can see some wooden flaps on the side of the windows. These are ventilation flaps. This is what we use to bring in fresh air during the winter and during the summer. These are automatically controlled by our building software management and building software. It's quite intelligent. So in the summer, it's not really important. The day temperature is not really important to us. What is important is the night temperature. In Middle Europe, we have about like 15 to 10 degrees lower night temperature than day temperature. And this is enough to cool the building. In the night, the flaps open, cool fresh air gets in, and this is our supply of cold. And this is what we use to cool the building down. And because of the masses inside the building, we can store it. And the building is very inert to this. Well, let's show you on the slide. All right. As you see, of course, it's a Bureau of Architecture, so it's quite fancy. The building is a mixed typology. This doesn't only work for offices or housing. We have a yoga studio, we have a gym, we have a plastic surgeon, apartments, and of course our offices there. So it's really neutral in its use. And this is quite important for us to be neutral. Because I don't know what the use will be in about 50 years. Maybe Braunschweiger Ebel or the Nödl will not exist anymore. But because of our neutral layout and the optimized geometry, we can put a kindergarten in there, for example. And this is a really important topic for all the architects. We have to build neutral. This is quite important. A hospital, for example, when it won't be a hospital anymore, you have to demolish the building because it's not neutral in its use. So, the building, just for example, is 24 by 24 by 24 meters. So it's quite compact, which is important for us. It's 6 floors high. As I said, we have 2 bricks there. And it will last a long time. About 100 years or more. It is quite simple, as I said. And this is why we can reduce life cycle costs. By a lot, actually. So what we do is, my team and I, we help architects or developers to create such a building with no heating, no cooling, and no ventilation. For example, we look at all the weather data on a specific place, we collect the data, we look at the geometry of the building, how can we improve it, how can we make it more compact, how can we make it more neutral. And then also, so I can talk a lot, but you have to have a proof of how, is this working actually? And this is why we do a simulation of the building. So it's a thermodynamic simulation, not a standard static simulation like in Passive House, but a thermodynamic simulation. So we build a 3D model of the building, then we put all the data we collected beforehand, so like the weather, solar radiation, etc. And then we simulate it from January 1st to December 31st. The whole year in a 2-minute rhythm. So it's quite a lot of data actually, and we simulate it in 3 stages. So just the empty building, then the building with the internal use, and the internal loads of course, and then the building with the internal loads and our operating system. The operating system always measures the CO2 content, the temperature and the humidity. And this is quite intelligent because it knows when to open the flaps if the CO2 level gets too high. It knows when to close the flaps, but you can open it also. So we replaced hardware with software. And this is quite impressive for me. And I think this could be a part of the future of architecture and of energy management inside buildings. Thank you.